picking up things, they have a target, they have a specific knowledge on what to go into. So it's more differ from your normal traditional programming. So in the traditional programming, in this aspect, we give the computer clear instruction, step-by-step rules, plenty of conditional statements, for loops for what to do. But with machine learning, we give it examples and data. Then we allow the models to figure out the patterns on its own. So the model here is more of like a self-learning. So when you provide the instruction to it, and the model tends to understand everything, and whenever you bring new data, it tells you what you need to know about that particular data based on its past history. So you can view machine learning as a subset of artificial intelligence. So AI. Underneath, we have inside, we have a machine learning data concept, machine learning logic built inside. Then we have under the machine learning, then we have a deep learning working inside. So the deep learning part, we won't go deeper into the deep learning. So it's just more of like being able to perform tasks that you can't use on classical machine learning. So the goal of ML is to improve the model performance as more data becomes available. Every minute, every second, millions, billions of data have been generated. So we need a concept, a model that can understand this data. We have plenty of data, numerous data being generated every second. So we need to understand, we need to be able to get the data, get the insight, allow the data to work for us, and whenever we have new, so that by the time we provide our own input, we can get data from, we can be able to get reply, get prediction on the model based on the historical data. So down to types of machine learning, we have supervised machine learning. So machine learning itself is generally divided into three main types, though there are kind of books that you can find something like semi-supervised machine learning, but in this distinct level, we have supervised machine learning, unsupervised machine learning, and reinforcement learning. So looking at unsupervised machine learning, here is a type of machine learning whereby the model learns from labeled data. So meaning every example, we already know the correct answer. So that is for supervised machine learning. The model has the features and the target or the label. If you can call it target, label. So you think of it like when you think of it back to the classroom scenario. You have we have the question and you have your answer. So if the lecturer is teaching, for every question given out or for every examples, there is an answer attached to it. So the answer is known as the label, the target to the features, which is the question. So the model sees the question and the right answer. So the model here as the student sees the question, you have the question and you have the answer attached to it. So you learn to predict correctly based on that. Next time when the lecturer brings up a question related to that, to what it has been, to what the student has been, he or she taught the student, the student can be able to deduce the correct answer on that. So predicting if an email is spam or not, this is because we have historical emails already and they're labeled. So we've already trained the data with many scenarios of emails along with the label. So we can have any email that has this particular type of link is a spam. any email that follows this first structure as a community email, as a community email patterns, or this is not spam. So we've already trained this model to follow this type of approach. So that is why when we are looking at supervised machine learning, we look at model that has question and answer type of data. Why for unsupervised machine learning is the type we look at, or is a type of machine learning that find patterns in an unlabeled data. This particular type of model does not have the label. The label is not attached to it. So you allow the model to perform the whole understanding patterns. So you provide the student the research statement or the synopsis for the coursework, or you give them the course content and you allow them to make research, find the patterns, find the answer to that. So you are only giving them the question, then you want them to find the patterns to find the patterns in that question and come up with the right answer. So this is the aspect of unsupervised ML. While for reinforcement learning, it involves agents learning to make prediction through reward and penalty. This is where you look at the types of robotics, self-driving cars, where you allow the model you allow the agent or the system to perform the task on its own, and you reward the model based on the right answer or the right move, and you penalize when it goes the wrong way. So looking at supervised machine learning specific, so like I said, it learns, the model predicts outcome based on input and output pairs. Then we also have when we are looking at supervised machine learning, the common application is your spam detection, where we are predicting if a model is spam or not, or it's case of diagnosing if someone is diabetic or there is a particular disease. So if this person is diabetic or not, or you are looking at in the banking sector loan defaulters. Okay, based on this particular person, based on this person transaction history, should we grant this person a loan or not? So, or based on these animal features, is this animal likely to be a cat, a goat, or a dog? So this kind of project scenario is known as the supervised machine learning, where you have your input, which are the features, then you have your output, which are the labels. So the quality of prediction depends heavily on the quality of label training data. So for your model to perform better, before you to have a good working model, you need to have a good data. This is where the aspect of data science, data analysis comes in. You need to clean up that data. Real world data is very messy. Very, very dirty. So unlike the ones you find on cargo that are already been cleaned up. So, but if you're working in a real world scenario, majority of the data is very, very dirty, messy, where you have data inconsistency, missing values, duplicates, and the rest like that. So you need to do a thorough EDA, also known as explorative data analysis, to clean up your data. For your model to perform better, you need to have a good data. So for example, if you're building a model to predict whether a transaction is fraudulent, so your data set will include details like the let's say transaction history, the return date, and things like that. Then your label will now contain will contain values like fraud or not fraud. So this person is likely to this transaction is likely to be a fraudulent one or not a fraudulent one. So the algorithm learns the relationship between the input and the correct output, so it can also make prediction on unseen data. So, like I said, the quality of the label data is it will directly affect the model accuracy. So when you're before you jump to building your model, you need to thoroughly clean up the data, get enough data so that the model won't overfit or underfit, and then perform the right feature engineering, perform the feature engineering in this case are the features that can help help the model to understand the labels, not some features that are not needed. Is more is for example, someone building if a transaction is fraudulent or not, or so let's say in an other health sector, you are building a diagnostic system that says if a patient is diabetic or not, then you are now having the features that are transaction record. So we can all agree that transaction record has nothing to do with if a patient is diabetic. So in this type of scenario, you can remove the transaction record and focus on the features that rightly answered the question. So down to supervised machine learning, it also can be divided into two main categories: classification and regression. So this whole supervised machine learning that we have been talking about, that has input and output. So you can also subdivide this into classification and regression. So for classification, you can view classification as when the output is categorical. So in this case, you are working on a discrete type of data, on a discrete type of label. So your label for classification must be discrete. You have spam or no spam, yes or no, good or bad. Is it a cat, a dog, or a goat? So but for regression, you have a continuous value. This value doesn't add, there is no end to it. So house prices, when you're predicting the house prices in a particular region in Eswatini, you know this kind of task, the label, the target won't be discrete. It won't be it won't be probabilistic. So it will be the range. You can have houses within 10 million, 15 million, 20, 50, 100 kind of million. So the price range is not discrete. You can also see it as from the temperature aspect. You're trying to predict a temperature. You can still, we all agree temperature is not discrete. Or you're working for an agricultural sector and they want to predict the crop yield. So based on their acres of land, the temperature, the humidity, the pesticide, the herbicide used, so they want to know the estimated crop yield. So this kind of task is known as the regression task. But in common, both tasks, classification and regression, uses a label data for training and they use the label data for training and performance to perform evaluation. So looking now, example of classification task here, we have your input data which help to define the categories. So the goal of classification is to assign data points into one of several categories of classes. So you can look at this example. Take the spam example. We have this particular table where we have email length, number of links, then you have the label. So here we have let's say we have a simple data set like this with two features and one label. So each email is a training set. Each email is a training set, and is labeled either a spam or not spam. So we feed the model, we feed this label into an algorithm, into our model, this old data, we feed it into the data, and the data tends to learn the patterns and help to predict whether a new incoming email is a spam or not a spam. So here you have email length. Let's say the email length is 120, the number of links is 8. Okay, the model learns that, okay, this is a spam. Okay, when the email length is 45, a new then the number of link is 1. This is not spam. So this data is serve as historical data for the model to understand. So it serves as all the old question and answering that's being done in the class. So whenever during exam period now, when a new question comes in, the model tends to understand, based on what it has been taught, it tends to, okay, when I have a pattern like this particular type of email length, this particular number of links, so this is likely to be a spam, or this is likely to be not spam. So for all these kind of tasks, common algorithm or common model used for classification include models like logistic regression. We have logistic regression. We have decision tree. We have random forest. We have SVM, support vector machine. We have KNN, k-nearest neighbor. These are just some of the most used model. We have several types of machine learning models that you can use for classification tasks. We have the Bayes, the Gaussian MB. We have SG boost, extreme gradient boosting. We have light gradient boosting, LGBM. We have cat boost. So we have numerous models that you can use to build a classification task. And in terms of application, we have email spam detection, we have disease diagnosis, we have sentimental analysis. Sentimental analysis in this case, where you have your textual data and you're trying to predict if this is a positive, negative, or neutral. For example, you are working for an e-commerce platform, let's say eBay, Amazon, or AliExpress, and you are trying to understand customers' reviews on a particular, let's say, vendor or a particular product. So you get their review. It tends to build if this review is positive, negative, or neutral. So the key here is that classification task under supervised machine learning deals with discrete output, categories that are separate and well defined. So, but for regression, you are looking at a type of task that deals with predicting a continuous numerical value. So let's say we want to predict the price of the house. Our data set might include features like number of bedrooms, square footage, location, house size, and the rest like that. So then the output will be the price of that house. So there will be the house price, which is continuous. So for example, looking at this particular table, you have house size 1,200, 1,800, 2,100. So the number of bedroom 3. So for this type of house, for this particular house where you have the size square feet is 1,200, number of bedroom is 3. So the estimated price is 250,000. Then for this particular house price, 1,800, number of bedroom is 4. The estimated house price is 350,000. So you can see that these prices here, they are not discrete. They are very open. So when you are dealing with continuous type of task, continuous type of label, you are dealing with regression supervised machine learning. But when you have a discrete type of label, good or bad, spam or not spam, fraud or not fraud, yes or no, or something that is more than this, that is not probabilistic, even if it is positive, negative, neutral, three values, you are still working under classification supervised machine learning. But when you get to the part whereby your label, the price here is continuous, the value is open-ended, so you are dealing with regression type of task. And the common algorithm that you can look at here is linear regression, ridge, lasso, decision tree regressor, random forest regressor. Almost some classification, some model we use in classification tasks also have their regression version of it. Decision tree regressor, we have decision tree classifier for classification tasks, decision tree regressor for regression tasks, random forest classifier for classification task, then the regressor for regression task. So and we are dealing with regression. You can use when you typical use cases of regression task is when you are dealing with when you're predicting financial, we are predicting financial forecasting. When you're dealing with financial forecasting, you are dealing with sales prediction. Will be, let's say, the sales for this month or for the year or for this particular quarter. So you are dealing with risk analysis, stock trend, temperature, energy demand prediction, or crop yield. So all these kind of tasks that have an open-ended label is what we use regression tasks for. So in short, we have classification answer what class, and regression answers how much. So when you're dealing with this should be classified under where, under what, then you are looking at classification task. But when we are looking at how much or the estimated number, then you are looking at regression task. Please, are we together? Please, can you still hear me?
Yes, we can.
Okay, thank you very much. So that is on the part of supervised machine learning. Again, supervised machine learning, when you're looking at it, it works with labeled data. So for supervised machine learning, it works with labeled data. You have this data, your data set has the features, and then the label. So here for this regression task, you have house size, number of bedroom as the features. Then you have the price as the label. The same thing for classification, email length, number of links as the features, then label as the label, if the email is spam or not as the label or target. So these are what you can find under the supervised machine learning. Down to So now let's talk about unsupervised machine learning. So for unsupervised machine learning, it is a type of machine learning whereby the model finds structure in data without any predefined labels. This type of machine learning, there is no label. It's like pushing someone into the bush for, let's say, treasure hunting without map. So you allow, or let's say you even provided map, but you want the person to understand the map, then go to that particular location. But for supervised machine learning, you push the person into the bush, and you also give the person the specific location to find the treasure. Why for unsupervised machine learning is just you provide the data without the label. There is no label for this. So you align the model to find the label by itself. So yeah, for unsupervised machine learning, the goal isn't to predict something, but to discover hidden patterns or grouping. I say clustered, yes, like that. So Unsupervised machine learning is just to find the hidden patterns in that data, because here there is no label. So you are allowing the data, the model, to find the patterns, to find the whole insights about that data and come up with something well structured. So, for example, you can think of a retail store that wants to segment its customers into categories based on their shopping behavior. So, let's say Amazon, or let's look at a big store that have customer data, but they want to group their data, they want to group their customers based on shopping behavior, so that they can know how to target the discount rate to each of the customers. Customer that gets up to, so a customer that buys products more than 1 million should be under type A. The one 50 million should be type B. Here there is no label, not like type A, type B. You only have customers, the ones with 50 million, the one with 100 million, the one with 1. So you have this customer record, but there is no label. So we let the algorithm, your model, to discover the patterns, like, oh, customer who buy kids product, customer who buys 100 products of 100 million should be under this, customers who get this should be under this, or those who shop during this scenario, during this time, should be classified under this. So the model will be the one to understand these patterns. If you look at the
Sorry,
image
this.
here,
Please share your screen. I think I'm not seeing it.
okay, let me reshare again. Please, can you see my screen now?
Yes, yes.
Okay. So looking at this particular image, we have this unlabeled data, scattered shape, triangles, we have the circle, we have the square, or should I say rectangle there. So this is how the data is being given to the model under supervised machine learning. There is no label. If it should be under supervised machine learning, we already labeled it that, okay, all the triangles should be labeled triangle, all the circle should be labeled circle. But under supervised machine learning, there is no specific label. They are all scattered. So the model will be the one to understand the patterns in this data set, then structure it. So at the end, we now have all the rectangles, all the triangles, and all the circles in a structured way. So this is how we looked at unsupervised machine learning. So under unsupervised machine learning, the two most common unsupervised machine learning techniques we will be looking at clustering. So clustering here is grouping similar data, similar data point together. For example, what we have here, you have your square, you have circle. So we are grouping data that have similar data points together, all the rectangles together, all the circles together, all the triangles together. So this is done under the clustering aspects. So here you can look at models like K-means clustering, hierarchical clustering for these. And we also have what we know as the dimensionality reduction. So for dimensionality reduction, it helps us to reduce our data complexity while you keep the essential information, the essential structure. So you can have, let's say, features, or you can have data sets with thousands of features, hundreds of features. So you want to get a concise form without losing any information. So with dimensionality reduction, it helps you to bring your data from a higher dimension to a lower one without losing any information. So here you use models known as the PCA, principal component analysis. So this kind of model helps you to reduce your model dimension, your model size, your data size. I mean, your data size from the initial plenty of features to a concise number without losing any structure, without losing the structure of the data or the information. So unsupervised machine learning is also used when you're dealing with anomaly detection. Doing anomaly detection, recommendation system, and topic modeling. So recommendation system I made mention of Netflix. When you watch a movie, they give you recommendation based on what you watched before, what you watch, or based on what other people that watch the same movie with you do watch. So they all when you shop on any e-commerce, they tell you people that shop for this product also go for this product. So this kind of recommendation system are classified under this unsupervised machine learning part. So when you're looking at supervised machine learning, is about prediction, while unsupervised machine learning is about discovery. So, but the third one, which is the reinforcement learning, is the type of machine learning that let's say is quite fascinating, whereby you have an agent that learns to make prediction by interacting with an environment, and you receiving the feedback in the form of reward and penalties. So that is how you have a reinforcement learning. You think of it as a try and error issue. So the agent tries different actions, observe the results, and adjust to its behavior to maximize the reward. So, for example, your self-driving car, you put your self-driving car in an environment, or your robot let's use a self-driving car in an environment. So you have different blockage for the car to maneuver. So whenever the car performs the right move, there's a reward. So with that reward, the car tends to understand that, okay, since I'm rewarded I was rewarded when I performed this particular move, I think this one is the right move. So it keeps saying that. But the moment it performs a wrong move where there's a penalty for that, it's it automatically knows that, okay, this is not the right move, because when I move this way, I was penalized for that. So it goes for the right one. So this is how reinforcement learning work. As for example, we are building game, or we are building a robotic system. So reinforcement learning is used in this kind of feed, game AI, robotics, trading system, recommendation platform. So in all these are type of scenario cases where reinforcement learning is applied. So it is a type of learning that is closest to humans and the animal actual learning. So whereby they learn through experience. We humans, the animal, we learn through experience and feedback, and from that we have a continuous improvement. But you can also, this particular part, you can view it when a child is trying to learn how to walk or learn to maneuver things. So whenever we have a fire, so if he or she mistakenly touches it, next time it's learned that, oh, this stuff, the last time I touched it, it hurts me. Then through experience, feedback, and continuous improvement. So now we've been talking about machine learning, supervised machine learning, looking at
Facebook
reinforcement learning. So now let's look at the model part itself, the algorithm, what the algorithm that helps us to understand this data. the algorithm that you provide your data set, and it's it learns from the historical data, whereby when you provide new input, it predicts the output. So what are these algorithm itself? So we are going to go through this each of the most used algorithm, and then how you can come up with the right algorithm, and when to each part of algorithm, or which part of model, or which type of model to use in which type of task. So understanding the fundamentals helps in effective model selection and tuning. So here we look at models like linear regression, one of the simplest algorithm. Relationship between your input and your output. So your input and your output, your target your target output. So it's easy to interpret and works when relationships are linear. When you're dealing with a linear type of task, where the model follows a linear approach, y equals mx plus c. For people that have mathematics background, making sure you understand the equation here. So for linear regression, when your task follows a linear approach, then linear regression tends to perform better in this case. And let me give you a scenario of how linear regression can be used, or a situation where we have a linear model. Let's say expenses rate and the income level. So when the expenses rate increases based on the income level, then we can tell that it follows a linear approach. For example, someone earning 1 million, then the expenses rate is like 700, 800, 900. The moment the salary increase, the income level increases to like 5 million, the expenses rate also increases. So in this case, you are having a linear approach. So the more the income, the more the expenses rate. So for linear regression, it assumes a linear relationship and minimize the sum of squared error. So it's simple, it's easy to interpret, and is effective for continuous outcome prediction. So here is a type of model or type of algorithm you can use for regression. You can only use it for regression task, predicting house prices, temperature, sales values, forecasting trend, and the rest like that. Provided it follows a linear approach, you can build the model you can build your model with linear regression. So another type of metrics we will be looking at is decision tree. So decision tree is a type of classification, is a type of model that handle both classification and regression task. So this type of model splits your data. It splits the data based on feature values, forming a tree-like approach. So the one thing about decision tree is that it's easy to interpret. So let's looking at this data. There we have weather. So is like you doing an if else statement based on your day-to-day activities. You're about to go out and you look at the weather. Okay, the weather is sunny. We are checking if the weather is sunny, cloudy, or raining. So if the weather is sunny, you look at the humidity. You drill down to humidity. So from the humidity, you look, do we have a high or a normal one? So if it's not high, then okay, I'm not going out. Let me stay. If it is normal, okay, let me go. Let me go shopping then. Or let's say if it is cloudy, you say okay, let me go. Let's enjoy the weather. Or if it is raining, you look at the wind. Is the wind strong or weak? If it is strong, okay, I'm not going out. If it is weak, then we're not going out. We are lucky. Let's explore. So your no, yes are the label to this. The no and the yes are the label you are working on. Should I go out or not? So now you now have series of instructions in your on the tree, where you have from the node to the leaf node, then to the down to your target, your label. So you are trying to predict the whole case scenarios to come to explore before you can come up with the right label, no or yes. So this is how decision tree tends to work. From your label, it tries to build a tree-like approach to it. If you look back to our data sets here, email length, number of links, label spam, not spam, spam. So what decision tree does is that it takes your data, okay, the email, okay, the email length. If the email length is 120 and the number of links is 8, okay, this is spam. Then draw down or let's say if the email length is greater than 100 and the number of links is greater than 5, okay, this is spam. If the number of link is less than this particular value and the number of link, the email length is less than this particular value, this is not spam. So this is how decision tree builds its own structure before it can give you a good prediction. So prediction tree is one of the most common used model across classification and regression tasks. It's another one challenge. One of the biggest challenges of decision tree is that overfit. It's easy to overfit. It can overfit. So overfitting is a common challenge to it. So that in that case, this is why we have the pruning techniques in decision tree to overcome that issue. So we have the pruning techniques that overcome the issue of overfitting here under the decision tree. So we won't be able to look deep into how all this model work theoretically. We can only just scratch the surface, but you can also make some do research before you pick up any model, understand the theoretical level of that model. Why should I use it, and how should I use this model? Though in the hands-on part, we will explore how to call call the model, then fit our data into the model, and use the model for prediction. So another type of model we'll be looking at is SVM, support vector machine. So for support vector machine, it finds the optimal hyperlink that separates classes with the maximum margin. So support vector machine, it finds the best, let's say the best possible line or boundary. So support vector machine find the best possible line or boundary that separates different classes. So for support vector machine, they are great for high dimensional data like text or images. When you have data that have a high dimension, so we can use a support vector machine for that kind of data. So it also handles both linear and nonlinear type of data through the kernel function. So it has a parameter that you can adjust based on the type of data you are working on. If your data is linear, you can adjust the parameter to a linear so that it can follow the linear approach. And if you have a nonlinear data, then you can adjust the parameter to follow a nonlinear approach, either a polynomial approach of different degree. You can have a polynomial of degree 2, quadratic, cubic, and the rest like that. So for support vector machine, it can also be used in both classification and regression task. So you have you have a support vector machine for classification, and you have a support vector regressor for regression tasks. And this is effective when you have an high dimensional kind of data. Then we have another one is the k nearest neighbor, known as the KNN. So the KNN is also known as the lazy learning algorithm. Very, very lazy. It classifies a data point based on how its neighbors are labeled. So it's very simple to implement and makes no assumption about data distribution. So what K nearest neighbor does is that let's say we have two groups, group A, group B. Then we have new inputs or new student that comes into the classroom. So the what K-nearest neighbor does is that it will look where the student is and the features that which features of that student is closer to any of the type that we have. The moment is if it's closer to type A, so just classify the student to type A. If the student features is closer to type, just classify the student to type B. So looking at this image here, we have the blue group, the team blue and team red. Here is our new data point, the query data point. So you can see that this query data point is closer to team blue, which here it has been classified to team blue. This is before training. You have a positive review, you have a negative review. So new user submitted a review. So we are trying to see, is this review positive or negative? Based on the distance, we are able to classify it to positive. So that is how k-nearest neighbor work. Though in terms of distance, there are several kind of distance metrics in place for this. We have the Euclidean distance, we have the Minkowski, we have the Manhattan distance. So there are distance that are put in place before it tells to classify a new data point to a specific data or to a specific group. So it depends heavily on choice of K and the feature scaling. So like I said, we won't be able to go into we won't be able to go deeper into each of these model to understand their concept, but we'll just scratch the surface. Another model which I think I skip is random forest, one of the most popular type of model. So random forest is like decision tree. It has multiple decision tree. It's like having this decision tree multiple times inside a single model. So random forest combines multiple decision tree, and random forest is also known as an assembled model. It follows an assembled approach. It helps to overcome the issue of overfitting that we're having in decision tree. So the random forest approach reduces overfitting and improve prediction accuracy. It's like we are building on the concept of decision tree. So another type of model is a neural network. So for neural network, it is inspired by the human brain. So this consists of interconnected nodes. We have all these zeros, the yellow, blue, green, red, are known as the nodes. So decision tree work like it works perform based on how the human brain works. So based on the interconnected nodes, they can learn very complex and non-linear relationship. So they are the foundation of deep learning. So in the next phase of this learnathon, we'll be looking at the deep learning part of it. So on that we are going to explore deeply of what neural network is. So now we're looking at the evaluation. You have your data set. perform the audio necessary data exploration and data preprocessing. You build this model. Now you are trying to see, is this model okay? Can we move this model to production or not? Is this model predicting right? Or is this model overfitting or underfitting? So here you need to evaluate the model. The same thing what is being done for GPT, and then before they chunk out this model out there, they tends to on this they tends to tell what evaluate them, benchmark them, and see if the model performs better. Should we release GPT 6.0, or should we release Cloud 7.1, or Sonnet 7.1? So they need to evaluate the model. So looking at classification type, I mentioned, if you remembered, I mentioned before that the metrics you use for classification is different from the metrics you use for regression. So under classification, we have a metric known as accuracy underscore, or you can just say accuracy. So for accuracy, what it does is that it takes the overall proportion of the correct predictions. So it looks at the model and takes the overall proportion of the aspect of the model prediction that were correct. So it looks at only the correct prediction. It doesn't look at the negative part, or the one that the model does not predict correctly. So looking at the formula parts, though, except you want to understand the underlying logic of all these models or metrics, we already have the package that you can just call, and then everything you can just initialize, and you use directly without worrying about this whole formula part. So, but as a machine learning engineer, you need to understand the underlying concepts of any model or metrics you want to use, so that if there is a need to tweak the parameters, you know where to go to. You know where to go, and then you know how to adjust. So, but for accuracy, it works best when your classes are balanced. Balance in the sense that your label data your label data, let's say spam or not spam, have a balanced number, let's 50-50. There is no bias or no oversampling. In this case, so not that the number of spam is 10 and the number of not spam is 40. So when your classes are balanced, then you can use accuracy. You can use the accuracy metrics to evaluate your model. Another metrics is recall, also known as sensitivity. So for recall, it tends to predict. We use it when you want to evaluate, out of all the actual positives, how many did the model correctly identify. So you can say we are looking at a scenario whereby, okay, we have positive, we have actual positive, we have negative. The actual positive, that is the one that are positive. First, we have the first negative, the one that that the model predicts negative, but they are not. So for to recall, what the recall try to evaluate the model on is that it measures how many of the actual positive were correctly identified. So in this case, when you have a high recall, it means that you have a fewer false negative. And the important is when missing a positive is costly, then that is when you tend to evaluate your model on recall. When you don't want to, when you're working with a sensitive task, you're working on a sensitive task whereby you don't want to make mistakes. In the health sector, you know health sector is one field that you need to be careful with what you are bringing out. So you need to be seeing it deals with someone's life and death. So it's very sensitive. So when you want to make sure that anything that is positive is truly positive, not that is somehow kind of positive, or let's say is 80% or 70, 60% positive. It should be truly positive. When anything you want to release is truly positive. So the more you want to release this model and you want to make sure that what the model is returning is truly positive, then you evaluate the model on the recall. Or you can also, based on this other name, sensitivity. So it's very sensitive. So you need to be very, very sure of the model outputs. Then another metrics is precision. So for precision, you are trying to predict out of all positive predictions, how many were actually correct. So you are indicating the proportion of true positive among all the predicted positive. So you have plenty of true positive, plenty of correct prediction, but you want to know how many of them are actually correct. So in this case, we can use the precision metrics to evaluate the model. You have a formula, true positive divided by true positive plus false positive. So here, where high precision means you have a fewer false positive. So it is useful when the cost of false positive is high. So in terms of spam filtering. So lastly, we have F1 score. So F1 score here known as the harmonic mean. So it's the harmonic mean of precision and recall. So it takes the harmonic mean of precision and recall. And it is useful when your classes are imbalanced. With accuracy is when the classes are balanced. But when you have a type of data that the classes are not balanced, then you can use F1 score to evaluate this the model prediction. So let's say you have a class whereby the yes is 10, the no is 40. So you're having an imbalanced data set. So one of your go-to is F1 score to evaluate the model. So please, are we still together? Betty, can you hear me?
Yes, please, we can hear you.
Okay. So another type of metrics when it gets to regression parts is mean squared error. So this is different. This is different from when you're dealing with classification tasks. The metrics for classification tasks are way different from when the metrics for regression. So under regression, we look at the mean squared error (MSE). So the mean squared error, it takes the average of the squared differences between your actual values and the predicted value. So the actual value is the one that you shown the model, the one that your actual value, the correct answer, and the predicted value is the one that the model predicted. So you are trying to check the error, the error value between them, between these two. So we have the MAE. I think there's a mistake here. So we have the penalize large errors more heavily. So when you're dealing with mean squared error, it penalizes large errors. So the more the output tends to zero, the better the model. When you're having results that are that when the evaluation result is like 50 or 10, the model tends to better. Or let's say you have two evaluation metrics, one is 100 or one is 150, the other one is 50. So the one with 50 tends to predict better than the one with 100. So then we have the mean. This is the mean. Mean. Here is mean absolute error, then mean squared error. So average square differences. Then we have the root mean squared error, which take the square root of the mean, the square root of the mean squared error. Then we have the R squared. R squared works like the model evaluation in class under classification, where you have your model predicts between 0 and 1, or between 0 and 1, that is 100%. You can have model like 0.7, 0.9, 0.8, 0.4. So the more it tends to 1, the better the model. The same thing goes under the regression task. Your R squared performs it measures the proportion of variance in the dependent variable explained by the model. So the values ranges from 0 to 1. The higher, the better. The more it tends to 1, the better the model. Please, are we together? So a quick one before we look at the end-to-end machine learning project workflow. Basically, is the comment section active?
You mean the chat?
Yes.
Yes, yes.
Okay. I want to ask like 5 questions, and based on that, the question is just about a particular task. Then I want everyone to comment what kind of task is that. Is this a classification task or a regression task? So then, let's go with this first. If that task is a classification task or a regression task. So should I type it here? Let me not type. Let me type it here. So let me stop share. So the first task here is, let's say you are given a data set of features like you are working with an housing company, and they said the country has their machine learning and data science engineer, and they're like, we want to know the selling price, or you are working for a real estate company and they want to know the selling price for each of the buildings there. So is this a regression task or a classification task? I will be in the chat section waiting. I just need up to like 5 answers. We are working for again, the question is, you are working for a real estate company and they want to know the selling price. So is this a regression task or a classification task? Okay, yeah, regression task. Exactly. Thank you very much. Since we are all following. So another one is you have a data set contains hours of students, numbers of assignments completed, and attendance rate. So you need to predict the final score out of 100. The goal is to predict students' exam score. So is this a regression or a classification? Student score. Yeah, is also a regression task. So lastly, before we proceed, we are working for a telecom company. You are working for a telecom company in Eswatini, and you want to predict whether a customer will leave the company within the next month. So you are trying to predict if the customer will leave the company within the next month. So what kind of task is this? Yeah, classification task. Exactly. Thank you very much. So now let's proceed. So we have before you embark on any machine learning project, you need to follow some steps. You need to follow some steps to achieve this in working on a machine learning project. First, before you even start looking at anything, you need to understand the problem statement. Identify the goal. What are we working at? What is the whole flow? What kind of task is this? Okay, this is a classification task. What type of model are we using? Okay, this is the model. So how are we going to evaluate this model? Is this kind of task, is the data available? So, okay, yeah, this is the goal. We want to predict this, we want to predict this, we want to predict this, we want to classify this, we want to build an estimated value for this. So, on problem definition, you need to thoroughly define the problem, understand the statement, the problem statement, understand every aspect of that project before you even start looking at it. Then you proceed to data collection. Okay, is the data available? Yes. Okay, now how can we get the data? Is it by data? Is it by mining? We're scraping the web for it, or is there a vendor that we can go to get this data, or how can we, or should we go with a questionnaire, so a survey approach, giving people we give out a survey for people to fill out, then for us to get the data, or how do we get the data? So the under data collection part is where you define the whole data collection procedure and collect the data. Make sure that every aspect of the data collection part is being covered. Then we have the data preprocessing. Now you have your data sets. You need to preprocess it, clean it. Like I said before, real world data is very, very messy, very dirty. Not all real world data will come clean. Some will not be consistent, some will contain missing values, some will contain rows that need column that you need to restructure and guess like that. So under data preprocessing, you need to clean up this data, make the data readily available to perform further analysis on. So for data preprocessing, you need to do audio adjustment, uh, uh, and then cleaning under this. Then we have exploratory data analysis, where you perform your EDA. You perform the EDA, try to explore the data you explore this data for further inform to get more insights about this data. Okay, look at correlation. Are these features correlated with the label, or are we having an outlier in this data set? Should we looking at the concept of this particular feature to this particular one? So under the data explicit analysis, this is where you go deeper into the data to explore, to get more insights about that data. Check for correlation, check for outliers, the duplicate address like that. Then visualize your data to communicate your data much better to the stakeholders. Then you have the model selection. You have the model selection, please, there's a mistake here. So model selection is now, in this phase is where you now select the appropriate model for this task. So under the model selection, you have you look at it. Okay, this is a regression task. Now, what kind of model should I use? Is this old data? Does this data follows a linear approach? Should I use a linear regression, or should I use a decision tree regressor, or should I use a random forest regressor, or should I use a use a SVR, that is support vector regressor, or should I use a light GBM regressor? So the under model selection is where you start start looking at, okay, based on the data and the analysis I've done so far, and based on the kind of task I'm working on, I'm going with this type of models. Then you have your model training and evaluation. This phase is where you train the model with your data and you validate it. You make sure that this model is okay to go to production. Then you have a model deployment. So now in this model evaluation, you make sure that the model is okay and is performing well. There is no overfitting and there is no underfitting. So now you push the model to production. It can be your housing prices model for them to predict house prices. It can be your email. You're working for Google Gmail team, and then you want to upgrade their email spamming. After training the model and validating that the model is good, then you push to production. You deploy it so that when they are using it, when email comes in, the model tends to classify if this email is spam or not. Or if you are building for agricultural sector to tell if a crop, to estimate the estimated crop yield. So after training and validating, evaluating the model, you push to production. You put it so that farmers can use this model to quickly get estimates of their crop yield before they start doing the whole plantation. So they get their acres of land, they get the number of seeds, they get the herbicide, they get the temperature and the rest like that. Then they pass all this into your model, and the model gives them, okay, based on all these features, your estimated crop yield should be around this particular value. So though it doesn't stop at model deployment, we have model monitoring. So you've deployed the model, you need to monitor the model for issue like data drifts. So data drift in this, for example, we are working for a real estate company, and you build a model to give estimate house price for users. So your job for the industry is that build a model that when the user comes in there and they say that I'm looking for I need to get a house with these particular features, number of bedroom, number of toilet, number of this, then what should be the price? And the moment you build this model, the period you build this model, that particular estate or that particular land is not developed. It's not yet developed. There is no much infrastructure on that land. So that was when we built this model. So we deployed it. The model will be predicting based on the fact that the land is still not developed and there is no much infrastructure, so the price will be kind of lower. So now, after 2, 3, 5 years, we now have much infrastructure, the industries, companies, and the roads, better road on that particular land or estate. So or around that estate. So in this case now, the model will keep predicting based on the past data, but whereas there should be the issue of ground is that we now have much development on within that housing estate, which means we need to update the model data. So this issue of data drift, the data there whereby the past data is no more reflecting what we have in the present. So monitoring the model will make you to quickly identify this issue and then retrain the model with the latest data. So you retrain the model with the latest data, then deploy it again. So we have, after model deployment, we have model monitoring and model maintenance. As a machine learning engineer, you need to understand that after your task doesn't stop at model deployment. You still have to maintain the model. You still need to monitor the model and see how the model performs over time. So I've been mentioning overfitting and underfitting all this one. So a key goal in ML is generalization. So making sure our model performs well not just on training data, but also when we pass unseen data to the model. There are times that your model can just perform better on the training, on your training data. It just when you give it to it, boom, you see 100%. But when you now pass new data, when you pass new data to it, it starts performing, it starts giving output that doesn't reflect the user input. So in this case, your model is having generalization issue. So now we have overfitting. Overfitting occurs when your model, overfitting occurs, it happens when your model memorize everything in that data, including the noise. Then at the end, when you now provide new data, it start giving you poor output. It's like giving your model an image to predict if this image is a dog, or you are giving it an image that contains an animal. So you're trying to trying to tell that the model, you're trying to tell the model to predict if it is a dog or a cat. So during the training time, the model has already learned everything about all the provided images that was used during training. It learned everything, including the noise, the color pattern, the stone on the floor, the background, everything. So the model is too complex. The model is too complex. Lion. So now in this case, it's reducing the generalization. So at the end, it tells the model start performing poorly. So another scenario is a student that memorizes past exam questions. He or she went to the library, takes past exam questions, memorize everything. Now, during the exam day, the lecturer decided to do some adjustment to the question, and the lecturer provide a new question. In this case, now the student cannot undo the new question, but he was able to understand the past questions, but it can't undo the new one. So this is an example of overfitting. The model is able to understand the training data, but when it comes to new data, it starts predicting rubbish. But for underfitting, you have when it happens when the model is too simple. Overfitting is when the model is too complex, it learns everything. But for underfitting is when the model is too simple to capture the data structure. So in this case, it doesn't even learn the basic. In terms of underfitting, the model did not even learn the basic pattern in the data. So you just like put you just give the model some data, and you don't allow it to learn very well before using the model for prediction. So that is issue of overfitting and underfitting. Though this issue can be controlled. So this issue can be controlled by techniques known as cross validation. You do regularization. So pruning decision tree. When you're doing decision tree, you have the pruning, and we have using more data. If you want to handle the issue of underfitting, you can provide more data to the model. So when the data is not that very much, the model tends to underfit, or the training size is not that very you are telling the model to, you have 1 million of data, and you are telling the model to just iterate over it 2 to 3 times, which is not enough to understand the underlying patterns in that data. And you can have simplifying your overly complex data models to avoid the issue of overfitting. The model should not be that very complex. So we have what we know as bias and variance trade-off. So the whole idea is that you need to balance your bias and the variance within the model. So balancing bias and variance is one of the biggest skills you will develop as an ML engineer. You need to find an equilibrium between the bias and the fitting, variance of fitting, so that your model can perform better. The model will not be overfitting nor underfitting. So one skill you need to handle very well before you can start building production-ready model is to make sure to handle the issue of overfitting and underfitting, the issue of bias and variance. Is a way together.
Yes,
That is,
we are.
okay. So we have the next phase is the model selection. The model selection part and the parameter tuning, where your model selection is an experimental process. Take that somewhere, put that somewhere. Is an experimental process. There is no one size fits all model. Not that okay, I use it because I use this model now and I perform better. It means that it will perform better in another type of data. So there is no one size fits all model. So we choose our model based on the nature of the data, based on the problem type, and based on the desired trade-off. For example, if you need interpretability matters when you need to be able to interpret the model. So we might use simple models like decision tree, linear models like logistic regression, linear regression for it. But if accuracy matters, we might look into ensembles methods and then look at the deep learning approach. So you need to understand the type of data you have, the type of task you are doing, and the complexity before you go ahead with the model, before you choose or select any model for your task. Why once you select a model and you perform you have your base model. After building your base model, you want to start adjusting the parameters. We have what we known as we move to what we call hyperparameter tuning. So under the hyperparameter tuning, you are adjusting the settings. You are adjusting the model. It's just like adjusting the buttons in the model that affect the model learning. So you are trying to tune the model parameter, the number of samples, the learning rate, and things like that. You adjust it so that you can have a better model. So they can have better accuracy. So that is where the parameter tuning comes in. So this can be done manually or through automated search. So you can adjust the parameter manually, doing some guesswork, try and catch error, or you can do some automated search using library like grid search or random search to iterate through the whole model and some parameters and pick which of the parameters brings out the best out of the model. So if you are able to perform this tuning, a proper tuning can drastically improve your model performance. And it's like tuning on, for example, it's like tuning an instrumental before a performance. So you need to make sure that everything works well. So if you're able to get the proper parameters, it can drastically improve your model performance and accuracy. So one of the challenges in machine learning, when you look at real world challenges, machine learning is very powerful, but is not magic. So machine learning is very powerful, but it's not magic. It's not something that you just give A and it just starts. So there are some issues, there are some things that you need to put in place. The quality of your model depends on the quality of your data and your understanding of the problem. If you're working on a machine learning project, the quality of your model depends on the quality of the data and your understanding of the problem. Here, if we look at some key challenges, we have data quality, whereby you doing garbage in, garbage out. If your model is biased, or there is an high variance, or the model is incomplete or unrepresentative, your model will reflect that, which means the model will not perform, the model will not predict well. And when we look at issue of bias and fairness, models can unintentionally discriminate if the training data reflects human bias. So this is why this is a growing area of ethical AI research, which Joe also mentioned. We need to build a responsible model, a responsible AI, where we need to put ethical AI research in place. We need to build model that is not biased, model that go with the ethical approach, that go with the whole policy of the whole for the whole ethics of the work. We need to put in data governance, data privacy and governance in place. We need to put data governance in place to make sure that we are having a model that is fair and does not discriminate, or the model that is not biased. Then the next one is the interpretability, where you have a complex model like deep neural network, which often work as a black box, but making it hard to explain decisions. So some models are too overly they are too complex that it's only the technical people can understand the whole work, the whole theoretical part of that model. But when you give that same model to someone not that is not in the technical space or a machine learning engineer, it tends to not understand how the model performs or how the model works. Then we have the model drift, the one I mentioned earlier, when your data in the real world changes over time. So what works today may not tomorrow. So you need to have regular monitoring and retraining. So back to the real estate, the model that works in the past, the data that work in the past may not reflect what will work tomorrow. So we need to keep data model monitoring and maintenance in place, so that whenever we have issue of data drift or model drift, we can adjust the model or the data to reflect the present real world case. So to succeed in machine learning, you must combine technical skills with domain knowledge, critical thinking, and then ethical awareness. As a machine learning engineer, you need to have a thorough technical skills with a domain knowledge. The domain knowledge may be kind of let's say not really needed, but still, if you have a domain expert beside you. So if you have a domain expert to guide you through the whole phases, then you may decide not to go deeper. But it's best to, before embarking on any machine learning project, you need to have knowledge about that task, that domain, be it health, fintech, finance, agriculture, education. So you need to have a domain knowledge about that, and also be curious and have think critically, and also you need to also combine your technical ethical awareness. So we need to build a model that is responsible and that is fair, and a model that does not discriminate. Okay, so and that wraps up the theory part of workshop. So we now build a strong. I'm sure we've understand and build a strong foundation of understanding machine learning concept. So in the second phase, which is the session 2, and this of this workshop, we move to the hands-on part where we get our hands dirty and lead some small machine learning model and deploy, which we'll be using Python for. So we'll be using Python scikit-learn, also known as sklearn, so to build a simple machine learning model across across the supervised machine learning type, classification, and regression. So in the next part, we will train and evaluate model in Python, and we will see all these concepts in action. So starting from how you get some data, to data preprocessing, to model training, to model evaluation, how we call all these evaluation metrics, down to how you can save your model and deploy. The quick one for model deployment, it also depends on the, let's say, the company and how you want to deploy. You can deploy the model as an API, and you can deploy it as a web app. But here we'll be using a web app, then we will save the model and integrate it into our Streamlit. Then you can see how it works on the web app using Streamlit. So so thank you for staying through this first section. Now let's take a quick 1, 2, 3 minutes questions before we move to the next phase. Please, any question? Now, for the Python part, you don't need to install, except you want to make use of, I've said, Cedric, how to get the Python for, unless you want to make use of your system directly, but you can use Colab.nodes, I think. You can use Colab. So with Colab, you don't need to install Python. You can just make use of Google Colab. So it has an inbuilt notebook already. Let me share this link. Colab.google. Okay. So the main difference between AI and machine learning, AI is more of like the umbrella of this whole let's say industry. So AI is the general concept. So inside AI is now where we have different domain. We have the machine learning, we have the data science, we have the deep learning. We are under machine learning, we now have deep learning. So AI is just the general term for everything. So inside AI now we start having machine learning and the rest like that. So yeah, to overcome the issue of scarcity of data, as primary data mostly seem to be unreliable. Yeah, data is, especially real world data, is very, very scarce, and then laying your hand on it, especially how some people do safeguard and store the data. But I think one of the way you can overcome is if you source this data yourself. You can do some scraping. You can scrape data, get in this data, you can scrape online, or go to a survey approach. That is a questionnaire, get people, allow people to fill up a questionnaire that you can get insights from. You can use as your go-to data, where you can start analyzing. So one part is you can source data yourself. You can scrape using Selenium, Playwright, or you can perform a survey or questionnaire, or also you can check some open source data repository like data.gov, do cargo to practice with, or you can also generate, if it's for practice sake, you can generate synthetic data to quickly work with and get your hands dirty. But in a real world cases, you can check open source data directory where most researchers, that there are several researchers that are already in the field of data collection. What they do is just they curate data, so you can check. We do research on data that have been created, and then work on. I remember we have this Karagal AI where my team and I work on the crop cocoa disease prediction to predict cocoa in terms of farming. So we were able to get real world data, and this is because that is because the data is the real world data that was created by some amazing Africans. Then we were able to, they were all data creators. So with their own knowledge, we added to our own machine learning aspects, and we were able to come up with a good model to work well on the agricultural sector. I hope I answered that correctly. Please, any question? Yeah, we still have 3 minutes to take up any question. Okay, so I assume no question. So for everyone, you can go to Google Colab. You have your notebook this way. We have a notebook this way. Okay. But we have the notebook. So first step where we'll be working, the task we'll be working on first is the one on, the first one is on the agriculture, we're working on agriculture sector. Let me put a mark down here. Let me just switch to this. Please, can you see my screen here? Can you see my VS Code?
Yes, we can.
Okay, so let me use this. Let's say, let me name this agriculture. Don't worry about the difference in environment. We are still working on the same notebook, IPYMV. We are still, you can see, I also have my own cells and the rest like that. So we have, let's name this agriculture. Agriculture. We have agriculture, then we have a predict crop yield. So we'll be working on regression tasks first. Predict crop yield. So here is a regression task. So the goal of this, the problem statement is that we are working for an agricultural company that tends to get estimate crop yield based on their plants, based on what they planted. So with this, we want to make sure that we are able to predict the estimated crop yield based on the rainfall, based on the fertilizer, soil pH, and things like that. So I'll be using the synthetic data, a quick synthetic data, and for those that want to skip the parts for data generation part, you can make use of. Okay, I think that has been sent to the group. So you can go to the drive, download the two data sets that we'll be using. We have the synthetic agricultural data and the diabetic data. So you can quickly make use of that. So first, for me, I know you can see I don't have my data, so I need to perform data collection. First, I've understood the whole problem statement. That's okay. We want a model that can predict copy based on the features, and then we should be able to deploy. So the model should answer some question. So first, we'll be looking at we'll be setting a random seed. Let's say np.random. First, we do data collection, my bad. So step one, we do loading. Step one, we do step one, we import. So it's best to always import all your libraries at the beginning. So we have step one, import all necessary libraries. Import all necessary libraries. So under the step one, we'll import NumPy. NumPy is also known as numerical Python for people just starting out with Python. NumPy is known as numerical Python and is used for vector matrices analysis, manipulation, arrays. So you can use NumPy. Then we have imports. Then as NP is the alias, so I don't want to keep writing NumPy. So I just shorten it to NP. So instead of me writing NumPy, I just use as NP. I just use NP directly. Then we have import pandas as PD. We have import pandas as PD. So pandas is a library that is used for data manipulation, where your tables, for your tables, you're trying to analyze your table, manipulate your table, either adjusting, getting the particular features. So pandas is one of the go-to. So there we have sklearn. So from sklearn, also known as scikit-learn. So you can sklearn. You can also call it scikit-learn. That is SCI-kit scikit-learn. So the name of the library itself is scikit-learn. So for importing it, we use sklearn. So from sklearn, so we are trying to use the model selected. So sklearn here is like, let's say, a big container. So inside that container, we now have different boxes. So that box is where we have one of the boxes is our model selection. So sklearn is the big container that houses this other method, model selection. Then inside model selection is now where we want to use a particular item called train test split. So what train test split does is that in our own task here, we do not have test data. Unlike some real world tasks where you have your training data and you have your test data. The training data is what you use for training the model, then you use the test data to evaluate the model. But in our own case, we do not have training data and we do not have test data. We need to make do with what we have. So which is to train, to be with the one with what we have, we will split it. So it's just like we don't have just like a time where we need to split the, or we don't need to split the data into two so that we can have train data and test data. But for some real world scenarios, you will have your training data, you have your test data, so you may not need to split. So for the model, we have from sklearn dot linear model from sklearn.linear model import. Since we are working with regression task, we'll be using linear regression. Though we'll try out other type of model from sklearn.tree import decision tree regressor. From sklearn.assemble import random forest regressor. So we'll be using these three models. Then for metrics, we have from sklearn.metrics import mean squared error and R squared. So these are the metrics we are going to use for this particular regression task. So now for the data part, we have step 2. Step 2. Step 2, data. Step 2, we have data collection. So in our own case here, we'll be using synthetic data. So we'll just generate a data with NumPy ourselves. So first, let's say we have np np.random seed for reproducibility. So for what this particular line of code does is that we set a random seed to make the result reproducible. Anytime we run this script, it maintains the same type of data that was generated at first. So in this case, random number generated by NumPy will be the same every time we run the code. So for the 42 part, that for the 42 that will pass inside is just an arbitrary number commonly used as a seed. So we can look at this particular line of code as locking the randomness so that your random data set can always be regenerated identically to always maintain the same thing. So next is we set the number of sample size that we want. So n, our number size equals 5,000. So we want 5,000 rows. So we want to generate 5,000 data samples. So each variable we have 5,000 rows. So our first variable is rainfall. Rainfall equals np.random.normal. np.random.normal. Then we have 600, or let's say we have 100, 1,000 comma. Let's just go with the suggestion. So this particular line of code, rainfall equals np.random.normal 1,300. So what it does is that it generates 5,000 rows, which is the n, which is the random values for a normal distribution or a Gaussian distribution, where the first value is the mean. The mean is 1,000 and the standard deviation is 300 mm. So for our normal distribution or our Gaussian distribution, the mean is 1,000. We are generating the mean is 1,000, the standard deviation is 300, and the number size is 5,000. So it represents the rainfall in millimeter. These are weighed together. So what this does is that most rainfall values will fall between will fall between if you are to use let's use a number that is very okay. Let's say we use 600 and we use 120 so that we can have a good output later. So what we'll be having here is a rainfall that we'll be having rainfall that falls between rainfall values that fall between 480 and 720. Though we can have some that can go higher or lower. So then our next feature is fertilizer. So fertilizer, we have, let's go with this. So for fertilizer, it generates usage in kg per acres. So we have fertilizer between mean of 100 and the standard deviation of 20. Then we have the next one, we have soil pH. So soil pH, you have between, let's say, 6.5 to 0.5, which is the pH level. So we generate pH centered around 6.5, which is an ideal neutral to ideal neutral to slightly acidic soil for crops. Then we also have the standard deviation of 0.5. So note that when you're dealing with pH, the pH scale typically ranges from 0, which is acidic, to 14, which is basic. So this is realistic agricultural data values here. So we have temperature. So we have temperature in Celsius. Then we have, let's just add some random noise to make it a little bit okay. Let's just add some random noise. Let's set this one so that will make it look more of like a real world. So it mimics what this does, that it mimics natural variability or the measurement error. So it's measurement error in real world data. So we just add that to it. Then next we have the yield alpha. We do the yield THP. So for here we have we are calculating the formula. This slide, it defines a synthetic formula for crop yield, that is ton per acres. So what it does, that we have is 0.05 times rainfall. So it's what this particular part means is that its yield, the yield increases with rainfall. Our yield value increases with rainfall, which means more rainfall, higher yield value. So we also have the fertilizer. So the yield increases with the fertilizer, which means more fertilizer, the more fertilizer we also have higher yield. Same thing with this part, the soil pH. It penalizes yield as pH move away from 6.5. The more it move away from the actual 6.5, the more the yield will be penalized. So the optimal yield will near pH 6.5. Then we have the temperature. So the temperature, which is slightly increased yield with temperature. So warmer to a limit, better yield. The more the temperature is warmer to a particular limit, we have a good yield. Then we add the noise. So we have the noise to it to add some randomness, so for it to reflect more on real world scenario. So that is on this part. So now let's create this data. Let's put everything together to form a complete data table. Then we have let's name it data. Let's do agricultural data equals rainfall. Rainfall, fertilizer, it's got this soil pH, temperature. Then we have our yield. So if we run this, we have our data ready. So now let's move to the second phase, which is loading our data. The third phase. So we load the data here. So on loading the data, like I said, if you remember, I said pandas is used for when you're dealing with data manipulation task. So you name for loading our data, we'll be using pandas. So instead of me writing pandas, we'll be using PD. So please, are we on the same page here? Okay, font size. What about now? Please confirm. Okay, thank you. So now let's load the data using our using pandas. So let's name the data frame df equals pd pd dots all. Before we even move ahead, so if you want to make use of this data later on, you can save it. So yeah, if you want to save it, we have agricultural data dot to save to CSV. So with this, you can save your data. Look here, we have agricultural data.csv. So if you want to save it, so you can save it. So now let's load the data, agricultural data dot add. So dot add helps us to view the first 5. If you're doing dot add, it helps us to view the first 5 of the data. So here we can do this. So we can see we have rainfall 659, fertilizer per kg, we have soil pH, we have temperature, and we have our yield. So what we are trying to predict. So you can see that it is a continuous value, so which makes it a regression task. And if you want to see the sample size, for the sample size, we have agricultural data dot shape. Agricultural data dot shape. Then you can see we have 5,000 rows and 5 columns. 1, 2, 3, 4, 5. 5,000 rows and 5 columns. And if you want to, let me add the comments here. I mark down. So, and if you want to confirm if there's any missing values, so you have dot is null, then we check the sum. So you can see all our 5 columns have zero missing values. So there is no missing values here. And to check for duplicate, duplicated values, If you look at it, there is no duplicates in our data. So we're having a unique type of data. So for each, these are data now, each represents a farm season with different condition. So you can notice how we define the relationship between the rainfall, the fertilizers, the temperature, the soil pH, and the rest. So this mimics the agronomic logic. Yeah, so the small random noise is just to ensure that we have something that is more of a real world scenario. So we can do some data visualization if you want to visualize this data. So you can perform some, this is where after knowing that there is no inconsistency in your data is good. So you can start looking at exploratory data analysis. You visualize the data, check for correlation. So you can check for correlation in terms of checking, let's say, agriculture data dot score. So yeah, you can check for correlation. We're having negative correlation here. So why we won't be worried about this one is because our data is not a reward, it is not, doesn't reflect the reward scenario. We are only working based on example case. So we just want to understand the underlying logic behind building a machine learning model. So it won't reflect more of the real world scenario. So from exploit the step 4, I think, yeah, step 4 is where you can do step 4. You start looking at uh, exploratory data analysis. So your EDA. So yeah, as a data scientist, journalist, you start doing, you explore your data, try to get insight, try to understand each of the features, and then look for outliers if there is outliers in your data. So outliers again, they are this type of data point that doesn't reflect or conform with what you have with the rest of the data points. So it's more of like, let's say somewhere a rural area where average salary, average salary is like 5,000. Then all of a sudden, we now have a machine learning engineer from
Sure.
outlier in that particular setting. So when you have value that doesn't conform with the actual distribution, so you have the outlier. So we are going to skip the exploration data analysis part. So we move to pre-processing part so that we can build our model. So like I said before, we only have a single data point. So this data point now this data point does not have we do not have test data or training data. So we need to split. So first thing is to split our data. And again, when you're working with supervised machine learning, you need to separate your dependent variable from your independent variable, your features, your variables from your target. So here now, our target is yield. So we are trying to predict. This is what we're trying to predict. This is our Y. Y, this is our S, our features. This is X1, X2, X3, X4. And this is our Y, what we want to predict. So first, we split our data into X and Y.
那我 OK 的解释，哎， usho ukuthi imnanzi kanjani.
So first we split the data, our X equals agriculture data
Madoda athela kangakazi ukuthi ngingasifani.
agriculture data dot drop. So in our X, we're only dropping this yield. So we don't want to make use of this.
Usho ukuthi nje leli tafula
So we don't want to make use of this dot drop. So in the dot drop, we pass this.
manje le bathroom kunani kunebhavu noma neshawa.
So then in our Y, we save this. So we are able to split this into X and Y. Our X, dependent variable and independent variable. Then in our X now, if you check the X.add, you will see that it only contains the features, the questions. So we only have rainfall, fertilizer, soil, temperature. So these are the questions. And here is the answer. And this is the answer. So the supervised machine learning will give you question and you have your label answer. You can see now, can you connect it with what we discussed during the theoretical section? So supervised machine learning, you have your question and you have the answer. See, we have our question, then we have the label, which is the answer. So for when you are doing supervised machine learning, you will have this. But if it should be, if it should be unsupervised machine learning, you won't have the label. You only have the question. So now to continue, now we split our data into training set and test set. Split into training set and test set, so that we can what we want to do here is that we have a subset of our data for training, and we also have a small chunk evaluating the model later on. So the training set will be the one to train the model with. The test will be the new data the model will evaluate on. So normally, like I said, for real world scenarios, you have your training set and you have your test set separately. So you can decide to train the model with all the old train sets. Then you have the test set to evaluate on. But in our own case, we do not have train sets, so we just need to make use of the one that except we want to generate another synthetic data separately for test set. But instead of that, we can just split. We can use this train test split function to do that. So we have X train. We have S train, which will be used for training. We have S test for testing. We have Y train, the label for training. Then Y test, the label for testing, which is equals to train test it. Then we pass our data, our X, which is the question. Then we pass our Y, which is the answer. Then we specify our test. We want to give 20% to the test size. So test size equals 0.2. So we are just, if your data is much, you can decide to give, let's say, 0.3. If your data set is up to like a million, so you can decide to give 0.3. You can do 70-30, 70 for training, 30 for testing. But in our own case, we only have 5,000, so we are only doing 80 for training, 20 for testing. Then the random state for reproducibility, so that anytime they run this code, it keeps generating the same thing and doesn't go outside the flow. So here now you can check, you can see strain.add, which is our training data. We have this. So you can see that the value is kind of not, we have a scattered data now. So if you do strain dot shape, you have 4,000. 20% has already been allocated for testing, then 80% for training. Okay, no questions for me. So please, if you have any question, feel free to drop it on the chat session so that I can go over it and then address that. So now let's proceed to the next step, which is I think step 6, model training. So now we've read from the beginning of this, from the problem statement, we've already defined the type of task we are doing, then the type of model we'll be looking at. So here we're looking at linear regression, looking at decision tree, and we'll also check the accuracy. So first, we look at linear regression. Linear regression model. So for linear regression, let's create a variable called linear reg. Linear reg. So linear reg. So we have linear reg, which is equal to, we call the linear regression model with, if you remember, we imported the linear regression model here. So we call the model linear regression. So after calling the model, then we fit the model. We train or fit the model. So which is the next step. So in the next step, we have linear our training set, S train, Y train into this. So here we already trained a machine learning model, a linear regression machine learning model. So if you look at the parameters that were used, the fit, insert, copy, X2, so these are default. We're only using the default parameter. So like I said, these are parameters under the linear regression that we can tune. We can tune so that to get the best out of the model. But for now, we are going with the default parameter of this model. So here, linear regression model. So we initialize the model and we train the model. So now let's use the model for prediction. Let's predict on the test data. So now the test data we have y pred, that a variable called y pred of LR equals linear regression dot predict S test. So we are now predicting on the test data. So we are the model. The test data is the data that the model have not seen before. So the model have not seen the S test before. So it's trying to predict on this S test. So now we can evaluate and see how the model perform. So we can evaluate the model. So if you remember, on our metrics we have mean squared error and R squared. So we'll be using these two for evaluation. First, we have MSC. Let's give a variable called MSCLR, which is the mean squared error. So mean squared error will pass the actual value this is the actual value, and this is the predicted value. So we are trying to calculate the error of this. So we can print. So we can print this. If we run this code now, we can say linear regression mean squared error is 0.17, which is a little bit, which is good. The more the error tends to 0, the better the model. Whenever you are using this type of accuracy, mean squared error (MSE), for mean squared error, the more the model tends to 0, the better the model. So you can, for those that will, for mean squared, let me just add a comment here. For mean squared error, the more the more the more close to 0, the better the model. So why for the R squared?
umuntu nase comfortable ne-rent akhona kuyibhadala ayamfuya asakahlala endaweni late titolo.
So why for the R squared?
Maybe itawusevelele mali.
The more the model,
Yeah.
So the closer the R squared value is to 1, the better the model. So you can see linear regression, we're having 0.99, 0.57, though we can't bank on this accuracy because the data is not okay. The data doesn't reflect reward scenario, so we may the accuracy is not with the accuracy, we can't accept the accuracy or use this model for a real-world scenario. So for real-world cases, we need to retrain this model on that particular data. So we need to retrain the model on the real-world data so that we can have accuracy that reflects real-world scenario. So this is for linear regression, 0.997. So if you are to check decision tree regressor. So for decision tree regressor, still follows the same approach. We may decide to use the default. Decide to use the default. We fit the model. We have the same thing. So these are the default value: criterion, squared error, splitter, best, mass. So these are the default value for this particular model. So we can use the model for prediction. Then evaluate it. So it follows the same approach with the first one. So that this is why machine learning tasks sometimes is easy to quickly adjust when it gets to the model because they follow the same kind of approach. So yeah, for decision tree, we have 0.17 for we still have the same thing. So we can have this. So for now, you can just you can let's not put more into the accuracy part. So this is because of the kind of data sets we are using. So if you look at the R squared too, kind of having the same thing, 0.957. So, but this is how you build your baseline model, your baseline machine learning model for linear regression, for random forest, for decision tree regressor. The same thing for random forest. The same thing for random forest regressor. So.
Manas.
Let's stick to the default value for now.
Manas, uzakhona.
If I had to train these two, I think we should be having the same issue. So though you can put all these in just one cell, but for us to be able to easily understand what is going on, we just want to That is why I keep splitting the number of cells to use.
Manas. Nitsin the girls are showering.
Okay, so that this for predicting on the test, so we can evaluate. So evaluating to evaluate the model, we can. Oops, we have this. So you can see there's a different, we have 0.4, which is different from what we have in decision tree and linear regression 0.1. So it shows that this is not this not much is there's a there we have difference between we have differences in the models. So here if we are to use the R squared, calculate the R squared, we should be having 0.9957, which is still the same thing with them. So in short, this is just we are just building a baseline model. So we can start looking at further on, we can start looking at building this, we can start looking at okay, how this model can be uh, tuned to perform better. So for now, we can just save the model, let's say best
Alright.
model.
Okay, Manas.
We want to save the model.
I was literally
So we have best model, best model equals let's just use the random forest. Best model equals random forest, then we can do let's say we have
yeah, but some was the man as bad no
let's
matter
do
no matter when the guy
let's just save it with job lib. Let's import job lib. Then we have job lib dot random forest. Then
okay.
we save our model so that we can use
I'm not
it
a boy
in
and go
we
WhatsApp.
can use the
I'll
model in
see
our
him.
Streamlit app. So if we save it, we already have. So for those
Yeah.
people using Colab, when you save, you will see your model at this part.
Okay, I'm fine.
You will see your when you open, you will see your model at this part. But you may not follow Streamlit may not run directly from your Colab.
Okay,
So
man.
due
I'm
to the fact
going
that
to
Stream
asifani
it run
one.
better
I'm
from
basically
script,
married to
so you may need
so
to switch
Western.
to you need to download the model and then
Sure.
switch to a normal
Yeah, yeah.
environment like
Right.
VS Code.
Sure.
So
Okay, man.
in
All
this
right.
part, we split the data into training set and test set with 80 to 80-20 split standard. Then we build linear regression, random forest, and decision tree. So then we have random. Then we save the model. So we save the model so that we can have a good so that we can have our model to perform better. So for in terms of overfitting and underfitting, we can try checking if the model, but there's tendency that the model is overfitting. So for us to start going to that, we'll start checking the training set and then check the log to see how it works. But for now, let's just proceed with this. We assume that the model is okay, our random forest model is okay and is production ready. So to move to prod, let me create a Python script known as agric.py. So here we import our Streamlit app. So here is the step 5. This I think step 7. Step 7. Streamlit app. So here we import Streamlit as ST, we import joblib so that we can use it to load our model, our saved model. We import joblib and we import NumPy for use. So before that, we have let's give our our web app title st.title agriculture yield let's agriculture crop yield prediction. So here is the title of the web app. Then we can add let's add something AI Eswatini to make it a little bit unique. So here followed by st.write. So st.write, so we can have enter the features. So we have a command, a prompt to tell the user to enter the features to predict the crop yield. So first we have our model. So we load our model from here. Model.joblib random forest. So since they're on the same page, so we load our model joblib. So then we have rainfall. We have rainfall equals st.number. So our rainfall will be in number, st.number inputs, st.number inputs. Then we have rainfall. Let's just go with this. So it will be the minimum value will be 0, the maximum will be 5,000, and the value let's remove a placeholder. So that we may not include a placeholder. Then the same thing for I think the same thing for how do we structure the data? Fertilizer. So the same thing for fertilizer. The same thing for fertilizer. The same thing for fertilizer. The same thing for soil pH. The same thing for soil pH. The same thing for temperature. So I think these are the 1, 2, 3, 4. These are the 4 features that we are using. Then we have an if button, if st.button, that means if the user click on st.button, it should then take the input features. It should take the input features. Input features equals to np.array. So we are converting all the stuff that the user imputed. We are converting it to np array, and then we pass everything into prediction for the model to predict. Prediction equals model.predict. So the model will predict the input features. Then we return an st success and tell them the estimated predicted value. We have estimated. Let's rewrite this one. Estimated predict crop yield. So estimated predicted crop yield. So is this. So now here comes the fun part. Now what we've done so far is that we build our model in our notebook. So this, as a machine learning, a quick one, as a machine learning engineer, your notebook is just for experimental purpose. So you need to go outside the notebook back to scripts for you to be able to deploy. So your notebook is just where you perform the whole analysis and the dirty work. So our notebook is where we are able to understand the data, visualize, do everything, build the model, do parameter tuning, and make sure that everything is working fine. Then before we now save the model and move the model for prediction for deployment. Please, are we together? Any question? Are we on the same page before we move to the next part? You can drop an emoji. Okay, thank you. So to run this now, we can have we can call the streamlit run app greg.py to see. Oh, my bad. Oops. Okay, so here we have agriculture crop yield prediction, AI Eswatini. So now let's say our estimated our rainfall. So this we deploy, we have this for the farmer. So when the farmer now, okay, the rainfall, let's say the rainfall is 100. So note, I'm just imputing a random value, not that it reflects what everything is. So my numbers may not be correct. So we have fertilizer, let's just say 100. So soil pH, let's say is 6.5. Then the temperature is let's say the temperature is 20. I just take this. So all this stuff, the moment you click on this predict copied, you are basically calling your model at the back. So the moment I click on copied, your model is the one doing this prediction. So you can see the beauty of machine learning. So when the user perform all this input and everything, and they want to clearly click on predict copy, they are basically calling the model you built at the back. So the model now is the one that performed this prediction. If I should change this to something like 500 and then change this one to like 200 or change this one to like 7.00 or change this one to like 30, then click on predict value. So we have a new value. So your model is the one doing this prediction at the back. So as a machine learning engineer, after you build this, this is a prototype. So let's just take the prototype as a full deployment. As a user keep using the model, keeps in them. When they click on predict copy, they keep calling your model at the back. So you can deploy the model as a normal web app like this, or we can deploy it as an API part where, let's say, instead of using this, what Streamlit does is that Streamlit helps us to provide us with the UI. So you can say we did not code this UI, but Streamlit is one that helps us with the UI. So let's say you are working for an organization that has a front-end engineer, so they have their own UI. So you just need to provide the model to the front-end engineer. So you need to deploy the model as a web app, as an API this time around. Are we together? But how many months does it take to master all this? There is no specific months, and there is no mastering it. I won't say mastering, but you can have a full concept about it. Let's say with dedication, 2, 3, 4, 5, but is a continuous learning. The tech field is a continuous learning stuff. You may not have to build the model, but there will still be a part that whereby you need to keep learning on how to adjust, maintain, monitor the model itself. So there is no specific one. It depends on how you keep upskilling yourself. So to new libraries and new packages that are being released every time. So there is no specific months. So due to time, we may not go to classification, but one thing you should know is that the classification part also follows the same approach. I don't know if I still have any little time remaining, but if not, for the classification task, it still follows the same approach. But the difference is that you are not using the same model. So you'll be using models like, for classification, you'll be using models like logistic regression. Logistic regression is the linear version of linear regression, but this one is for classification task. So you don't allow the regression part to confuse you. Then you have a decision tree classifier. You have random forest classifier. So for the metrics, you have accuracy, you have F1 score, and the rest like that. So this is for, you are dealing with classification task. So we may not touch the classification task. So you can, I've already provided the data set, so you can check the data set. You can, from the data set, check it up and see how to perform a classification task. So I will make this notebook and the script available with the drive, where you can just use it as a guide to have your own data set separately, and from there you can then make use of, you can build your own work on that. So we'll wrap it up here. Before dropping the mic and passing it to Bella, please, any question?
How? It is not here.
So we are free to any question, either from the hands-on part or from the section 1, which is the theory part. Please, any question? Okay.
Yeah, confused man. Okay.
I think I see a question here. What is the future of AI and ML in automation? For artificial intelligence and ML, they moving automation from simple, we have the rule-based task where you have the intelligent and the adaptive system. So for in terms of automation, they really have instead an aspect of the normal rule-based era, where you have scripts, macros, and the rest like that. So where automating form entries and reports are very hard. So, but now in terms of uh, AI and ML, they are really transforming the automation field very well. When you look into the aspect of intelligent process automation (IPA), you combines the rule-based, the ML, the NLP to handle complex and semi-structured workflow. So you look at example like automating your invoice processing, the chatbots, and the rest like that. So they really have, even when the aspect of predictive and prescriptive maintenance, model also help to predict when machines and system might fail. I have someone that work on the energy flow, which is a production ready task that has been deployed now, where it helps to calculate the probability of an energy failing, or the next fix for the energy sector part. So the test of, even we are looking at into software testing and DevOps, it works perfectly. And then they really have a brighter. So what is the process of evaluating a model when new data that may influence the outcome arise? So first, when you build the model at first and see how the model works in terms of in terms of the historical data. So it's how you see, it's how you look. You can have an human in the loop. You can have an human in the loop approach, whereby when the model make prediction, you monitor how the model predicts, and does it reflect the real world scenario. For example, back to the example, the real estate prediction we made earlier, the real estate scenario. So before, when you trade the model, the estate were developed. So developed. So when they are given, when the model now start developing, when you start passing new data after the estate has been developed, you can see that you looking at the output the model is giving out based on the new input. You can see that it doesn't reflect much, or it doesn't show that the model is reflecting on the real world scenario. So your human in the loop doing the whole data monitoring and maintenance should know that there is an issue from the model output, based on there is a model output considering the new issue we have on ground. So you can retrain the model and then reevaluate the model on that new type of data, so that whenever you have new data points coming in, it will reflect, and the model will perform better on that. Then how can we reduce bias and unfairness in model? For bias and variance in model to have a good bias trade-off, we have what we know as regularization. So regularization techniques, yeah, when it comes to normal classical machine learning, like the one we just classification and regression, when we build, we have what we know as the ridge L1 and the lasso regularization techniques, or the ridge regression and lasso regression. So they help you to balance your model in terms of underfitting and overfitting, bias and variance, high bias and high variance. And for neural network, we have the dropout layer. So we can introduce a dropout layer to help you to handle the issue of overfitting and underfitting. Or you can also add an early calling, early stopping, so that whenever the model is start going astray, then it should call back the model and stop the model at that particular part. So you can do regularization, you can do early stop, you can, if it is decision tree, you can do pruning into it and make sure that, or if its model is underfitting in terms of bias, you can introduce more data points to it to train it with it, and also you can also increase the epoch, the number of iteration time, so that the model have enough data point, not enough time to understand the patterns in the data set, and also enough data point learn from. So with this, you should be able to tackle the issue of overfitting. That is the issue of overfitting and underfitting, bias and high variance in your model. Okay, so I think that is the last question. Bella, Sam, Mr. Sharing here, over to you.
Okay, okay. Thank you so much, Aziz. Thank you so much, and thank you so much, everyone. I hope I am audible. If I am, please confirm just by a raise of hand or yeah, or thumbs up. Okay, I think we have a quite okay. Thank you, my bongwe. Thank you. Um, I think I did no introduction. My name is Samgailo Msibi. I am a representative of AI Eswatini and Africa Machine Learning Days. I am the carry apologies from our DA moderator Betty. She had other engagements and this session kind of extended. Um, I carry many thanks from the team, from the instructor as well. We are saying thank you for attending, and we hope that you learned a lot, and we hope that you will continue attending the series until it ends. Then I would also love to give thanks to our speakers and instructor. Um, most of you may not know, but they chose to volunteer at their time, their own data. So they chose to be here, and they chose to be here at no charge. So I just want to say thank you for them, and yeah, and please don't forget to fill out the survey form, and also please don't forget to fill the participation form. It will enable you to receive the certificate that you attended this session. Then if you will attend all of the sessions, the certificate will also include that. So that's it. That's it from me. I'm not sure if anyone wants to have a comment. In 5, 4, 3, 2, 1, 0. Okay. Thank you so much, people. Thank you for attending. Yeah, that's it. And we will try to post the recordings on YouTube. Please like and then follow our pages. So yeah, that's it from me. Thank you so much, guys. Meeting adjourned. Yes, my bongo. Yes, my bongo. Do you wanna say something? Okay, I guess not.